Welcome to This Explainer. Today, we're diving into a genuinely fascinating paper by Dan Adrian German called A Term-Rewriting Semantics for Pure Quantum States. Now, if you've ever felt totally locked out of quantum mechanics because the math just looks like an alien language, well, you're absolutely going to want to hear this. We're looking at a framework that's designed to make complex quantum computing universally accessible to pretty much everyone.
So, what if quantum computing only required middle school math? Seriously, take a second and imagine a world where that intensely dense mathematics, usually required to understand quantum circuits, is just entirely stripped away. Imagine grasping the fundamental logic of quantum computation using the exact same arithmetic you learned when you were like 12 years old. It sounds almost impossible, right? But actually, that's exactly the paradigm shift we're exploring today.
Okay, let's dive into Section 1, the quantum math barrier.
Conventional quantum physics presents this massive, highly intimidating mathematical wall for beginners. It's filled with equations that might seem completely divorced from the actual logical concepts you're trying to grasp. It literally stops bright minds right in their tracks. But the MISTY formalism, it bypasses that barrier completely. It relies on simple arithmetic, which makes it incredibly accessible to first-time learners without that huge wave of initial intimidation.
Which brings us to Section 2, Introducing MISTY States.
The evolution of this idea actually kicks off back in 2017. Researcher Terry Rudolph introduced this concept of MISTY states with a really noble goal, which was creating an elementary system to teach the basics of quantum circuits to middle and high school students. Fast forward to today, and Dan Adrian German has taken Rudolph's educational tool and significantly expanded the formalism to handle some seriously complex quantum phenomena.
So what exactly is a MISTY state? Well, at its core, it's what we call a term-writing system. That means it describes quantum states using a tiny, universal set of gates and basic arithmetic. You simply replace symbols according to specific logical rules. So instead of solving massive differential equations, you just follow a step-by-step substitution process. It's almost like a giant logical puzzle.
Now you might be thinking, okay, if it's just middle school math, it must be super oversimplified, right? Actually, scratch that. It's not. This system relies on incredibly robust mathematical results by Yaoyun Shi, and it leverages powerful theoretical work by Aya Kitaev. By standing on the shoulders of these mathematical giants, the MISTY formalism achieves good enough accuracy with only a small computational overhead. So it's simple on the surface, but deeply mathematically sound underneath.
Moving right along to Section 3, Simple Math, Universal Results.
Here is the truly mind-blowing part of German's paper, universal capability. You can literally use this to do any quantum calculation. This isn't just some toy model designed to keep kids entertained with a watered-down version of physics. No way. Because of the specific set of gates it uses, any computation a multi-million-dollar quantum computer can theoretically do, we can logically map out using the simple arithmetic of MISTY states.
All right, Section 4, Bridging to Advanced Theory.
Dan Adrian German is very clear in his paper about his ultimate goal here. He notes, and I quote, "The MISTY formalism can effectively be used to facilitate a transition to the full, conventional quantum mathematical apparatus." So he isn't advocating that we throw out conventional quantum mechanics. Rather, he's arguing that MISTY states are the ultimate on-ramp to get there.
It essentially acts as a perfect stepping stone to the heart of non-trivial quantum theory. And why does this matter so much? Because a learner can grapple with the non-intuitive logic of quantum mechanics, wild concepts like superposition and entanglement, without the intense cognitive overload of learning advanced linear algebra at the exact same time. You learn the quantum heart first and the mathematical apparatus second.
Let's look at Section 5, Extending the Formalism. To push this science forward, German takes 3 really deliberate steps in his paper. First, he reviews the strengths and limitations of Rudolph's original 2017 proposal. Second, he thoroughly tests it, showing it in action through a complex process called entanglement swapping. And finally, the real breakthrough, Step 3, extending the entire formalism by introducing a brand new category of states.
German's primary addition to the framework is this concept of irreducible MISTY states. In this term rewriting system, an irreducible state acts as a fixed point. Basically, it's a state that just cannot be further simplified or rewritten using the rules of the system. By defining these fixed points, German gives the MISTY framework a much more robust structure, which is exactly what allows it to handle advanced quantum scenarios without breaking down.
And to see exactly what those advanced scenarios look like, the paper highlights two key applications. First is entanglement swapping, which German uses to show the original proposal working perfectly in action. But even more impressively, he tackles the GHZ game. This is a famous thought experiment involving quantum entanglement between 3 or more parties. German successfully presents the GHZ game inside his newly extended setting using these irreducible states, proving for sure that this arithmetic-based system can handle some of the most mind-bending thought experiments in physics.
Which really leaves us with a final, provocative thought. If simple arithmetic and term rewriting can unlock the complexities of something as advanced as the GHZ game, what other quantum mysteries are out there just waiting to be demystified for the rest of us? Dan Adrian German's work proves that the barrier to entry for quantum computing absolutely doesn't have to be a wall of impossible math. Sometimes, all you need is a fresh set of rules. Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you next time.